An architecture model is kind of like the magic mirror in Snow White. So if you recall from the story of Snow White, the evil queen looks into the mirror and says, "Magic mirror on the wall, who is the fairest now of them all?" Doesn't that sound sort of like the question we ask of our architectures and our system solutions? Well, then there's another interesting thing about the magic mirror. It always tells the truth, but sometimes we don't want to know the truth, or we can't handle the truth. So our models can have value to the extent that they give us, at least get us closer to the truth, because these models are usually predicting the future. Will the solution we're designing actually solve the problem of a future we don't even know about? I mean, we barely know everything about the current situation, much less years down the road when our system will finally be deployed. So why do we develop an architecture for the system? Why don't we just go straight into coding or bending metal? Well, we do that anyway. But, so I'm often asked, by my program managers, when can you get the architecture done? Can you get it done by next Thursday? And I'd shake my head and said, well, we'll get some of it done, but it'll actually never be done because we're continually understanding more and more about the architecture. And we're not done with the architecture model ever, but we want the architecture model to drive the design model. And we want that design model to drive the test models and the manufacturing models and the operations models. So it's really a continuum, and the architecture model can always be used throughout the life cycle of the system. The system is part of a larger solution. Okay, so we kind of deceive ourselves by saying that we are going to just have an architecture of the system. But systems are always part of a larger solution, and there's some elements of that solution that are not systems at all. There's the natural environment within which the system resides. There's the things in the natural environment. There's the infrastructure it resides upon. There's the operators, the users who interact with the system. There's various other elements of the solution. But it turns out the system by itself has no value whatsoever. But the solution also has no value whatsoever by itself. Only when the solution is used in an enterprise context where it helps the enterprise better achieve its objectives for an affordable cost and acceptable risk. So when you talk about the value of a system model, well, the system itself has no value, but to the extent the system model tells you to what extent can the system contribute to that solution, well, the better it tells you that, then the more value your architecture models will have. And once you model the solution, if the extent to which the solution models will tell you of how it contributes to the value to the enterprise, and all the enterprise customers, in fact, it's the whole value chain of the enterprise, upstream and downstream. It's not just the customers of the enterprise. So we have a problem. If we rely on our models to tell us the truth, and our models are always wrong, that sounds like we have a conundrum. How can we rely upon models to tell us the truth about the future of our solutions and our systems if they are wrong? Well, I think the second part of that sentence is the hint. Even though they're wrong, we have to make them as useful as possible. But what does it mean to have a useful model? Well, one thing you can do is make sure every model can answer important questions for the key stakeholders. But what are those questions? You could open up the System Engineering Handbook and there's a lot of implied questions in every step, but those are system engineering questions. You want to make your models useful for all the disciplines and all the stakeholders. So it's a challenge figuring out what all the questions we want. And in fact, there's an infinite number of questions. You can never stop finding additional questions. You could. So notice the important word is important questions. So it's important to find out what are the most important questions at this point in time. Because it may be that there's other important questions 6 months down the road and 12 months down the road. So there's really a time series of important questions. And the answers to the early questions might lead you to ask different questions down the road. So the answers need to be accurate. Notice I said enough. You can always do more modeling, do more work to make them more and more accurate, but they just need to be accurate enough. And sometimes you need to do a quick and dirty model just to give us a quick and dirty answer so we know what question to ask next. But they also need to be timely. There's no point in getting a model that gives you the answer next week when you need the answer tomorrow. It's basically a worthless model, so it has to be timely. It also has to give you insights. It has to tell you things you wouldn't have known otherwise. Okay, and that's the tricky part, because that doesn't sound very mathematical or scientific. But it's almost like, when you have good models, you'll know it when you see it. You'll know it when you turn the crank and exercise the model, and it starts giving you answers that you can rely upon. But then you may not actually know if it's the right answer until you build and test and deploy something. But you want to know now. You can't wait until you deploy the thing. So what questions do we want to ask? Well, when we're modeling a system, it's usually, what is the system going to do? How well? And Ron was talking about these requirements, and the requirements often are an expression of what and how well. He even showed you requirement templates that get to those exact questions. But at the solution level, different questions like where, when, how will it be used? And he did talk about that. And that's kind of a different level. Sometimes they call that the operational requirements versus the system requirements. Okay? Or sometimes they call that the mission requirements or the mission engineering versus the system engineering. So how will it be used? And some of us, we would call that the concept of operations. In other areas, we might call that the business model. Or we might call that the value proposition. So how will it be used? We have different notions of what that means. At the enterprise level, it's a different set of questions. Why are we even bothering to solve this problem? Okay, so the system does this and that, and it does it this fast. So what? Who cares? Different kind of questions. Okay, since we don't want to just model the system, and we get those what and how well requirements, at some point we need to see if that system contributes in the best way to the total solution that contributes to usually one or more enterprises, because usually these solutions, in fact, it's desirable for solutions to be usable across many enterprises, because that makes a good business proposition and probably leads to better viability of your company and better profitability and all these other kind of things the enterprise managers care about. So one thing you could ask is, how well do our models help answer these kinds of questions? The heuristic we call the four who's. Who benefits from this solution I'm planning on delivering? Well, who loses? There's always losers, but we often don't think. We talk about benefit versus cost, but how often do we talk about loss versus cost? Well, we do talk about loss in terms of risk analysis, hazard, mitigation, threats, resilience, but that's only one category of losses. If we're going to automate something, what about the people currently doing that job? They might be losing their job, they might be losing their livelihood, and so on. Who's going to lose? Who's going to pay for this? I don't mean just who's going to write you the check for developing the system, but who's going to pay for the solution once it's deployed? They may pay in terms of quality of life. They may pay in terms of no longer being able to afford to live close to work, and they have to have a long commute. So there's many kinds of ways they can pay. And who supplies not just the thing you're designing, but who's going to supply the support? Who's going to supply the maintenance? Who's going to supply the decommissioning of that? Or who's going to supply getting rid of the waste byproducts from your system? And there's some other key messages that your models need to convey. And these are some of the questions you should ask. Does my models help me answer the question about how well do we understand the problem? Is the solution good enough? There's a trick. What does good enough mean? The models can also define what good enough means. And then once you have the good enough model, then you can compare it to the solution you're proposing and answer the question of how good enough will the solution be. Is it affordable and timely? Is the risk acceptable? So this is an example of, if you can ask these sort of questions of your models, then that will give you some hint about, are we having, are we developing models of an architecture nature that are of value? Because modeling is hard. It's an investment. So what we need to know about our project work is are we doing the right models and at the right time, and are they answering the right important questions that are important at this point in time? So there's some useful questions to ask before you even get to architecture. You have to ask questions about the business need, the mission needs, ask questions about the operational concept. This gets into those so-called operational requirements or the mission engineering. You need to understand functionally what the capabilities, not the physical capabilities. The physical capabilities are explored in the architecture itself. In order to deliver this operational concept, what functional capabilities do I need? And then once you know all the answers to those questions, then you can start into the architecture model. So architecture can tie it all together. Not just tie things between the system elements together, but tie the system to the solutions. And often our systems are part of multiple solutions, and that complicates things. We talk about product line management, and that's what you're talking about. Is we often put our system into various products in the product line, a family of systems, so to speak. So, yes, we have a lot of very common ways to portray different aspects of the system. We can talk about the parts, we can talk about how they're connected, we can talk about how data flow, we can talk about how the cyber attack can happen and get in there and do bad stuff. We can talk about all the piece parts and how they come together and how we're going to build this thing and deploy it. But that's only a few of many, many kinds of views we create from the models. So how do we do modeling? Well, SysML, of course, is designed for modeling the system. But what would a modeling language look like for modeling the solution? Will SysML be adequate? Because the solution is more than just systems. How do we model the enterprise? Can we extend SysML to do? Yeah, a lot of people have extended it. The DoD architecture framework is an example of an extension. But it doesn't cover all aspects of enterprises. It tends to focus on defense enterprises and military capabilities and effects and so on. So another thing that contributes to the value of models is the modeling ecosystem. You can be doing the modeling very well and producing very, very valuable, important models, but if you have better enablers like templates and checklists and modeling procedures, modeling techniques, those can help you create those more valuable models in less time, less effort. So these are the model management activities. So these are just some of the things that go on in the ecosystem of the modeling effort. And all of these things can contribute in one way or another to developing more valuable models. So George Box was a very profound thinker. So all of our architectures are they're fiction, but we want them to be a useful fiction. So they answer the questions that we as system engineers are asked by the program managers, by the business managers, by the users, by the operators, by everybody in the value chain will be asking us questions about what will this architecture do for me? How will it solve my problems? How will it avoid additional problems that might occur because you deliver that solution? So let me talk about one step in the modeling ecosystem called problem framing. I gave a paper yesterday morning about this, and the details of how to do this are in the paper. And the problem framing, there's 4 steps. First is, who is going to use those models, and how are they going to use it? Okay, so if you know who needs to use those models, or who can benefit from having the models in hand, and then you can start asking, well, what questions will they need to answer, perhaps with your models? So knowing the uses and users, boil it down to the questions, and also it's important to know when people are using the models, when they're doing their job, what decisions do they need to make? And every person has different decisions. Program managers have questions about how much money should I allocate to this particular element? How much time should I put on the schedule for it? What resources should I assign to these projects? But the architect has other questions. The operator of the system will have different sort of questions for the model. They want to know about usability, security, and so on. So the second step is identify the scope and context. The third step is information and data. In other words, you don't identify what models you need until the fourth step of problem framing, because you need to lay the groundwork. So here's a little bit more details about what happens in each of the steps. So the most important thing you should know when you're doing modeling is what decisions, either in my program, above the program, outside the enterprise, what decisions that need to be made that a modeling effort can help the decision maker make better decisions. How can we as modelers help inform those decision makers so their decisions are more timely and of a greater quality? So there's the uses and users, but once you know the purpose of the architecture in terms of those uses, then what issues need to be explored? What questions to be answered using the architecture? What types of analysis do you need to perform to start answering those questions? What are the interests and perspectives of the intended audience? So we often take SysML diagrams and show them to stakeholders and expect them to understand what we're talking about. So that's why I separate the models from the views, because views need to be human understandable. But we engineers fall in love with our model diagrams, and we're so proud of them. We spend a lot of time, we invest a lot of energy into our models, and then we start to, we're so proud of it, and also as engineers, we don't know how to translate that into business speak or into operator speak. So maybe we need to augment our modeling team with non-engineers who know how to communicate to all these non-technical people. So step 2 is, what's the scope and context? Are we doing this model that's going to be good for the next 20 or 30 years? Or is it just going to be a model we put together and answer questions next week that after that we can just throw it away? What's the context for the modeling? What's the context for the thing we're trying to model? And step 3 is, once you know what the questions are and the uses, what information do I need to come out of the models? In other words, the views that are derived from the models is where the information resides. So it needs to inform people. That's what the word information means. Data doesn't necessarily inform you unless it's translated into their language and their symbology. So the last step is where you start identifying, given those questions and that information needs, data needs, what models and views do you need? So we often we get so caught up in our modeling that we lose track of the real purpose of our modeling. We get so excited about the modeling tools, and we learn all kinds of new techniques, and we need to keep in mind what is the ultimate decision that you're trying to support. Because system engineers, the way they add value to system development is by helping people on the project understand what is the nature of the problem, what are some of the issues we need to address, and how does the proposed design solutions contribute to solving those problems. That's our job as system engineers. So we often make the mistake of running around, these mice are running all over, and yet that we're ignoring the tiger in the room. So hopefully problem framing can help you identify the tigers so you're not stuck spending all your time chasing mice. So architecture models have value if they can answer those fundamental questions of benefit versus cost for the key stakeholders, but it's also more than benefit, it's also the losses, who pays, who supplies, remember the 4 who's. But they also have value if they can do it in a timely and cost-effective manner with a minimum of effort. I mean, it sounds kind of easy, but all of us who do modeling know that's hard. And you should not even start doing any models until you know the questions need to be answered using those models and how those answers will help people on the project and at the enterprise level to answer their important questions. Thank you very much.